Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we're going to discuss week 1 our 2 tutorial for both NFTF and also FTF. So the learning objective for the non-face-to-face questions is for you to be able to write the rate law. So the rate law, we have already seen this in the video, the rate law with respect to the order of reactions. So these are the keywords, order of reactions. And then once you have done the rate law, then you need to determine the unit for each of the rate constants respective to the order of reactions. And lastly, you need to sketch the graph of the rate of reactions. So we need to do everything here for 0, first and second order. So for your syllabus, we only cover for 0, first and second order. So given to you these reactions from A to become product. So please recall that the rate law only involves the concentrations of reactants. So our reactants is only A. And then the order of reactions can only be determined via experiment. So you cannot simply take the coefficients given. Let's say you have 2A, so means the order of reactions is 2. No. This order of reactions will be given, or maybe they will give you a hint in terms of unit. So then only you can know what kind of order of reactions for these chemical equations. Alright, so since the questions ask you to write the rate law, unit of rate constant, and sketch the graph for all three order, then I have simplified into this table. So basically we have everything that they want: rate law, unit of rate constant, and also graph. And then we're going to do it one by one starting from 0th order. So let's start with the rate law for 0th order. So we know that the rate law is rate is equal to K concentrations of A to the power of 0. So we know that any power of 0 will give you value of 1. So we can simply discard this part and leaving only with rate is equal to K. So from rate is equal to K, we need to find the unit for the rate constant itself. So in order for you to get this unit of K, then we need to know the definitions of rate of reactions. So rate of reactions is basically changes in concentrations divided by time. So we know that our rate can be changed to this dA over dt equal to K. So this dA over dt represent the unit of K. So we know that concentrations is mole per liter. And then time, let's say we have time of second. So we have second here. So if we combine everything together, we will get a unit of mole per liter per second, or molar per second. And then for the graph, since rate is not dependent on the concentrations, means you're gonna get value of K which is remain unchanged throughout the reaction. So our y-axis gonna be rate, and then our x-axis gonna be concentrations of A. Since they are not dependent on the concentrations, they're gonna get K as constant. Alright, that is for 0th order. As for first order, we're going to write the rate law again, but this time around, our concentrations is raised to the power of 1. So rate is equal to K concentrations of A to the power of 1. So any number, any concentrations that is raised to the power of 1 or 2 or 3 or etc. more than 0, they will depend on the concentration. So we need to keep these concentrations in the rate law. So means rate is equal to Ka. you can cancel out the 1, or also you can keep it as it is. Next, we're gonna derive the unit of rate constants. So we substitute the rate with dA over dt. And then for k, we have Ka. Right. Now, if we substitute all the unit for this, then we're going to get mole per liter per second. Second is equal to K mole per liter. Okay. Once we combine everything together, then we're going to get K, since this mole, we're going to cancel it out with the next mole, so we are going to cancel this out, leaving you only with per second. So this is the unit for first order reactions, per second. And as for the graph, if I want to keep rate against concentrations of A, then I'm going to have my y-axis as rate, and then my x-axis is concentrations of A, since they are dependent on these concentrations. Means if we have an increase in terms of concentrations, means the rate will also increase. So they are going to show a directly proportional relationship. So this is your K. Alright, so as for second order, so we are going to write it as rate is equal to rate constant concentration to the power of 2. Okay, so now simply change the rate to become dA over dt. And then this one we have K A squared. Once we substitute the unit, we're gonna get mole. Okay, this time we try to use molar. Okay, we have molar. And then here we have, let's say we have second. And then here we have K. And as for the concentration, since we raised it to the power of 2, means we're going to have molar squared. Okay. So by bringing this K on one hand side, and then bring everything else on the right hand side, so we're going to have molar divided by molar square second. Okay, and then we're going to cancel out this molar and also one of this molar, means our final unit will be per molar per second. Or if we write as mole per liter, then it's gonna be liter per mole per second. Alright. Okay, so for the graph, although we have a number of graphs, maybe we can do it like 2 types of graph. But if I want to keep the y-axis as rate, while for x-axis, I want to keep it as concentrations of A to the power of 2. So because it will depend on the concentrations, so they are going to increase like double of them. Okay, so they're going to have a linear graph, directly proportional graph. So this is your K. Your shape of graph depends on your y-axis. If you want to make your x-axis become only A, then you're going to get quadratic graph. Okay, so that's all for non-face-to-face. So this is how it's going to look like. Okay, so let's proceed with face-to-face questions. So for face-to-face questions, you should be able to determine how the rate affected by the reaction constant. So we're gonna relate the theory we have already learned in non-face-to-face with the applications in terms of the value in experiment. And then you also need to know how to perform calculations using integrated rate equations. So these integrated rate equations is basically comes from the rate law. So what we need to do is you take the rate law with respect to the order of reactions, and then you need to do some integrations on it. But in our syllabus, we don't need to show the derivations of the integrations. We simply need to memorize how does it looks like, since you already learned it in your maths syllabus during high school. Okay, now, so look at the first questions. The reactions below is second order for NO and first order for Cl2. So it already tells you the order of reactions. Recall again that your order of reactions cannot be determined from the chemical equations. They will either tell you what is the order, or maybe they tell you the unit of the rate constants. So that's how you know what kind of reactions is this. So this is the most essential information that we need to have since we're gonna write the rate law. Okay, so now you know that second order is for NO, so this is second order, and then for Cl is one order. So overall order reactions is 3, so 2 plus 1 is 3. But in your syllabus, you only learn from 0, 1 and 2. But for overall order reactions, it can be more than that. Alright, so by what factor? So by what factor here is mean the multiplier of this reaction. So basically this factor is located at the rate constants. But then if they say increase, like these questions, they ask you to doubling both NO and Cl2, means you have to double at the NO. If they says doubling both NO, means this NO needs to times with 2, this Cl needs to times with 2. Means you're going to have 2NO, 2Cl, 2Cl2. Alright, since we already know the order of reactions, the first thing that we need to do for these questions is write the rate law with respect to the order of reactions. So you will write rate is equal to K, rate constant, to the reactant concentrations, which in this case is NO, and we know that our NO need to be doubled, so you must write 2NO. Alright, so we know that our NO is in second order, so don't forget to write second order here, followed by your Cl2. Our Cl2 is in first order. Still, we need to times it with 2 because this question asks for double the concentration. So, you must write 2 before Cl2. But now, your order of reactions is only 1. When the question asks for factors that increase the rate, means you need to take all these numbers, multiply with the power, or maybe, multiply with the power, and then brings all the number that you have calculate to the front, to here. Okay, to here. Right. So now we know that the 2NO is raised to the power of 2. So 2 to the power of 2, you're going to get 4. So from here, you're going to get 4NO square. Okay, and then from here to the power of 1, you're going to get 2Cl2. your order of reactions must remain unchanged like this. You need to keep it as it is. The thing that we need to take out is only this number, the 4 and also the 2. So we know their relationship is times. So we need to times 4 times 2, then it will be 8. So how are you going to write the final rate law? So you need to write as rate is equal to 8K concentrations of NO to the power of 2 concentrations of Cl2 to the power of 1. Alright, that's how it will look like. Next, we're gonna try for the second questions. Making Cl2 3 times higher. So we want to times this Cl2 only. They didn't mention anything about NO, so NO will remain as it is, so means times 1. Then Cl2 we need to times it with 3. So we need to first start with the rate law. So rate is equal to K NO square. Then for Cl we have times 3, so 3 Cl2 to the power of 1. Okay, this one we have to the power of 2, sorry. So we have 2. Okay. So now we have this 3 raised to the power of 1, so it will become 3, right? So then we can simply write the rate law as rate is equal to 3K NO to the power of 2 Cl2 to the power of 1. Okay, lastly, for question 3 Roman, making NO 3 times higher means we need to times it with 3. And then while halving the Cl2 means we need to make the Cl2 halved. So 1 over 2. Again, starts with your rate law. Rate is equal to K. So as for your NO, we're going to times it with 3. 3NO raised to the power of 2. And then followed by your Cl2 now is times with 1 over 2 to the power of 1. So we know that 3 to the power of 2, we're going to get 9. So we're going to have 9NO squared. And then for this 1 over 2, we're going to have 1 over 2 Cl2. Okay. So our final rate law would be rate is equal to 9 times 1 over 2. Then we're going to have 9 over 2K. And then simply copy NO raised to the power of 2 and then Cl2 to the power of 1. So basically, the factors given here that we have already found here, it tells you that the reactions is raised by these factors. So 8K times with 8 factors. So they increase 8 times. They increase 3 times. They increase 9 over 2 times, like that. Okay. Moving on to the next part. The conversions of cyclopropane to propene in the gas phase is a first order reaction with a rate constant of 6.7 10 to the power of -4 per second at 500 degrees Celsius. So you need to first extract the informations here. Conversions from cyclopropane. So we know that our reaction is going to start with cyclopropane, propane to become propene. Both are hydrocarbons with 3 carbons. Okay, so they already tells you that this order of reaction is first order. So we know that our rate law gonna be rate is equal to concentrations of, we know that we're gonna take only the reactant, so it's gonna be cyclopropane. Cyclopropane raised to the power of 1. If let's say the questions didn't tell you that this is a first order reactions, you can look at the rate constant here. This rate constant tells you that the unit is per second. So as we have discussed earlier, we know that the per seconds is belong to the first order. Alright, so given to you the temperature will be given to you because it is part of the conditions for a reactions to occur. Well, for A, if the initial concentrations of cyclopropane was 0.25 molar, so the information given here is initial concentrations, means we have concentrations of cyclopropane at initial states. So concentrations note. What is the concentrations? So they want us to find another concentrations, but only after this time. Means the time allocated is 8.8 minutes. So we know that this is gonna be T. Means the concentrations that we want to find is after certain period of T. The T is now 8.8. So this is our concentrations T. Alright, so the first question they ask for this concentration. The first question asks for concentrations, and then they further ask you what fractions of cyclopropane has decomposed in this time. Means that they want to know how much cyclopropane has decomposed from the initial concentrations. Alright, so now we need to look at which equations at which formula that we're going to use to find these informations. Can we use rate of reactions? No, since we have 2 types of concentrations, it is impossible for us to use rate of reactions. Can we use rate law? No, again, we have 2 types of concentrations now. So the only formula left is integrated rate law. So since it is a first order reactions, then we can simply take the first order of reactions integrated rate law, which is ln concentrations. For this time we're going to use cyclopropane, concentrations of cyclopropane at initial states divided by concentrations of cyclopropane after 8.8 minutes. So this is your time. So this ln A0 over AT gonna equal to KT. So let's check whether we already have these informations or not. Do we have informations regarding concentrations at initial? Yep, we have this. Do we have the time? Yep. Do we have the rate constants? Yep, we already have this, 6.7, 10 to the power of -4. So all left here is only our concentrations of cyclopropane after 8.8 minutes. Simply substitute the value where ln concentrations of initial cyclopropane is 0.25. Then we want to find the concentrations of let's say I use short form for this, CP, after 8.8 minutes equal to, our K is 6.7, 10 to the power of -4, times with, they give you 8.8 minutes, so I want to change it to second. Okay, I'll change it to second, so 8.8 minutes is equal to 60 seconds. So 60 seconds over 1 minute. So I'm gonna cancel out the units. Alright. So once we substitute this value and then we calculate the value, then we're gonna get concentrations of cyclopropane after 8.8 minutes gonna be 0.1775 molar. Okay. So now the questions ask you, okay, before I forgot, the reason why we need to change it to second is because the rate constants given here is in second. So that's why we need to standardize it to become second. So it all again depends on the questions. If the questions give you the rate constants in minute, then you can keep it as it is. But for this time around, the reason why we need to change it because the rate constant is in per second. Alright, so now we've got the concentrations of cyclopropane after 8.8 minutes. Now we need to find the fractions of cyclopropane has decomposed in this time. In order to know the fractions of cyclopropane has decomposed, we need to first subtract this value 0.1775 with the initial concentrations, which is 0.25. So we're going to write it as 0.25 minus 0.1775. So this is the concentrations that is being decomposed. Okay, right, so we're going to get 0.0725 molar. But this is only concentrations. You need to find the fractions of these concentrations. So again, in order for you to get the fractions that decompose, you need to divide it by the initial concentrations. Fractions decomposed is equal to 0.0725 divided by the initial concentrations of 0.25. Then you're going to get 0.29. Since it's a fraction, so we already cancel out the unit. That's why we got no unit for fractions. Okay, for the next questions, we have how long will it take for the concentrations of cyclopropane to decrease from 0.25 molar to 0.15 molar. So the 0.25 belong to the initial concentrations, while 0.15 molar belongs to the concentrations after certain times. So they want you to find the time taken. How long will it take? So means this is the time. So since it's still the same reactions, means we're gonna have a first order reactions. So ln concentrations initial divided by concentrations after certain time is equal to KT. Once we substitute the value, we're gonna get ln 0.25 divided by 0.15 equal to 6.7 10 to the power of negative 4 times with time. Alright, so we want to find the time taken here. So once we put all this value into the calculator, then we're gonna get 762.43 seconds. So this is your final answer for these questions B. Okay, next, for the last questions, it asks you, how long will it take? So again, they ask for time. How long will it take? So this is going to be the time to convert 74% of the starting material to propane. Means that the one being converted is 74%. In order to become propane, 74% of cyclopropane must decompose. Initially, we have initial concentrations of 100%, and then once it decomposes, we will have leftover of cyclopropane. How do we calculate this? So simply 100 minus 74, leaving us with 26. So only for the first order reactions, we can use this kind of percentage. So now we have the cyclopropane at initial concentrations and also after certain time. And then we want to find the time taken. So we're going to use the same integrated rate law, which is for the first order. So we have concentrations initial over concentrations after certain times is equal to KT. Alright, so simply substitute the value. So we're gonna have ln 100 divided by 26, okay, is equal to, we use the same rate constant, 6.7, 10 to the power of negative 4, and the time that we want to find. Lastly, we're gonna get T is equal to 2010 seconds. Okay, so this is our final answer. Alright, so this is the overall tutorial for this hour. So we have learned about the rate law and then the integrated rate law. Soon we're going to learn about the half-life and also method to determine order of reactions. So I hope everyone could do some revisions on this, because I'm going to give you homework on this weekend to see whether you clearly understand about this topic or not. Alright, so thank you everyone. Assalamualaikum.